Hello, class. In this video, we are going to go over section 2.5, which is going to be on the chain rule. So this is the idea of composite functions. So a composite function is where we have f of g of x is equal to f of g of x, based upon the way it's listed. So for example, capital F of x is equal to the square root of x squared plus 1. We could write this out as a function composition, where f of x is our outside function and g of x is our inside function. There are multiple ways to describe this. There is no such thing as a right answer. Well, I mean, there are right answers to it. But what I mean is, you don't necessarily have to abide by the same ones that I would choose for this, as there is more than one answer to this. But one answer to this is to take the outside function to be the square root of x, and the inside would be x squared plus 1 as our function composition. So, based upon this function composition idea, we have the chain rule. If g is differentiable at x and f is differentiable at g of x, the composite function, capital F, is equal to f of g of x, is differentiable at x, and capital F prime of x is equal to f prime of g of x times g prime of x. So based upon the Lebanese notation with y is equal to fu, u is equal to g of x as differentiable functions, dy over dx is dy over du times du over dx. So to give an example here, using that function from before, we're going to capital F prime of x, if capital F of x is the square root of x squared plus 1. So from this, this is the same thing, if it's helpful to write out, x squared plus 1 to the 1/2, right? So for us to do this, we would take this power that we have for the outside function, toss that in front, and decrease the power by 1. So 1/2 times x squared plus 1 to the negative 1/2 times the derivative of the inside now. The inside being x squared plus 1, we want the derivative of that, which is going to make just 2x. So slightly rewriting this a bit, it makes x divided by x squared plus 1 to the 1/2, or the square root of x squared plus 1, based upon this function. So this uses this power rule and the chain rule. I didn't show the substitution on it, which, I mean, you could if you wanted to do it. Not 100% necessary, just because you would have to do the steps anyway. But if n is any real number, u is equal to g of x is differentiable, then the derivative with respect to x of u to the nth power is n times u to the n minus 1 times du over dx. Or we could write derivative with respect to x of g of x to the nth power is n times g of x to the n minus 1 times g prime of x. Here's another example. Differentiate y is equal to x to the 4th minus 1 to the 100th power. So toss the 100 in front, subtract the 100 by 1. This makes 100 times x to the 4th minus 1 to the 99th power times the derivative of the inside, 4x cubed. And we could slightly simplify that to be 400 x cubed times x to the 4th minus 1 to the 99th power. This third one, I have find the derivative of f of t is equal to the 6th root of 4 plus the tangent of t. So f prime of t. Just to point out before I do this out, this is the same thing as 4 plus the tangent of t to the 1/6 power. So that 1/6 will come in front times 4 plus the tangent of t to the 1/6 minus 1, so negative 5/6 times the derivative of the inside, which will be the secant squared of t. So slightly rewriting this. This is the secant squared of t divided by 6 times 4 plus the tangent of t to the 5/6 power now, based upon this. Example number 4. We want the derivative of f of x is equal to 3x minus 4 to the second power times x squared plus x plus 1 to the fifth power. So this one's going to have a bunch of steps just because of how much this is. But make note this does use the product rule inside of it when taking these derivatives. If it's helpful, u is 3x minus 4 squared. So du will be 2 times 3x minus 4 times 3. So that would be 6 times 3x minus 4, so 18x minus 24, based upon what we have there. V is x squared plus x plus 1 to the fifth power. dv would be 5 times x squared plus x plus 1 to the fourth power times 2x plus 1. So can't really do too much in the way of simplifying that, but I'll write 10x plus 5 times x squared plus x plus 1 to the fourth power. So popping all of this into our derivative using the product rule, this is going to be, and then might as well, okay, did I need to do all the multiplication for that? Actually, it'd be probably nicer if I did not do all of the simplifying. We'll see why in a minute. Let me just erase these. Yes. All right. So this is going to be, well, I will multiply those actually. 6 times 3x minus 4 times x squared plus x plus 1 to the fifth power plus, this is going to be 2x, actually I'll multiply that by 5. 10x plus 5 times x squared plus x plus 1 to the fourth power times 3x minus 4 squared. The reason why I didn't start multiplying everything to simplify is because we're going to factor out a few things here first before trying to simplify. We're going to first and foremost take a 3x minus 4 times, we're going to have x squared plus x plus 1 to the fourth power. And that's going to leave us with 6 times x squared plus x plus 1 plus, we're going to have 10x plus 5 times 3x minus 4. So simplifying everything in the brackets, can't really do too much with the outside. 3x minus 4 times x squared plus x plus 1 to the fourth power times, multiplying the 6 and then foiling the other two binomial. This would give us 6x squared plus 6x plus 6 plus 30 x squared plus 15x minus 40x minus 20. And then just slightly combining a few terms in our bracket. This makes 3x minus 4 times x squared plus x plus 1 to the fourth power times 36x squared minus 19x minus 14. That's our complete answer based upon that. We could also use this with division. G of y is equal to y minus 1 to the 6th power in the numerator. Denominator is y squared plus 2y to the 7th power. So this one functions in the same idea as the last one, where I'm not going to simplify this too much. Let u here be y minus 1 to the 6th power, and du in our case would be 6 times y minus 1 to the 5th power. Times 1, but that doesn't change the answer, so I won't bother writing it. We're going to let v here be y squared plus 2y to the 7th power. So dv is going to be 7 times y squared plus 2y to the 6th power times 2y plus y. And so, because of that, I'm just going to multiply this a little bit. 14y plus 7y plus, I made a mistake, just plus 7. There's no y here. This would be a 1. 2y plus 1 for that derivative of the... I made a mistake again, goodness. The derivative of 2y of y squared plus 2y is 2y plus 2 here. So multiplying that by a 7 would give us 14y plus 14 times y squared plus 2y to the 6th power. All right, so popping this into our formula for the quotient rule is going to give us g prime of y is, this is going to be 6 times y minus 1 to the 5th power times y squared plus 2y to the 7th minus, we're going to have y minus 1 to the 6th power times 14y plus 14 times y squared plus 2y to the 6th, all divided by, this would be y squared plus 2y to the 14, to the 7 times 2, so 14. We could factor slightly by taking out y minus 1 to the 5th and y squared plus 2y to the 6th times, this is going to be 6 times y squared plus 2y minus, we would have 14y plus 14 times y minus 1. Still all divided by this y squared plus 2y to the 14th power. We could slightly simplify by canceling out a little bit with the denominator and simplifying instead of the bracket that we have. So y minus 1 to the 5th times, just to point out what I'm doing very quickly, this disappears entirely, and this becomes 6 minus 14, which will make an 8. Anyway, y minus 1 to the 5th times, this is going to be 6y squared plus 12y minus This will be 14y squared over minus 14y plus 14y minus 14. But since we had a negative in front of it, that'll be a plus 14. All divided by y squared plus 24, plus 2y, excuse me, to the 8th power. And then we could slightly simplify a little bit more in that numerator to be y minus 1 to the 5th times negative 8y squared plus 12y plus 14, all divided by y squared plus 2y to the 8th power. So let me know if you have any questions or concerns. Thank you.